right? The same thing. And then again in this lateral direction, also get shrink, so negative. Are we okay? Yes.
The loading piece of X, how's it going to?
The loading. Can you say that a little bit louder?
Does there need to be an area under the loading, or?
The area under the loading here.
Yeah.
Yes, that divided by A, cross-sectional area. For example, this is a cross-sectional area A. Okay?
Okay.
Yeah. Okay. So now we proceed to the next loading type. For the next one, so in the next one, we consider is in the y directions. We applied as defined as our axial directions. In this direction, we consider another loading, which is, let me call the py. So by repeating the same reasoning, right now we shift our focus to the y direction, which is our axial or loading direction. So for this case, we apply the loading in y direction. This will induce the stress in y. So sigma y will become our axial stress. Okay, and again, the calculation is simply PA divided by PY divided by I, divided by A. Okay. So right now, let me mark it. So for this second loading case, y will be our axial direction. So let me mark on here. Okay. So let me mark on here. Y will be our axial direction for this loading case. Okay. So in the axial direction, let me draw this again. So right now, let me utilize this model one more time by changing the symbols. That is, right now, y is our axial direction. That will corresponding to sigma y will be equal to this one. In the axial directions, the traditional one-dimensional Hooke's law apply. So that means here the strain sigma y equal to sigma, strain epsilon y divided by this one, right? In the y direction, the axial strain, right now for this case, is epsilon y become this. Are we okay? And now, respect to the y, then x and z is our lateral direction.
Would
So,
it be sigma y or sigma x?
oh yes, sigma y. Thank you. Thank you so much. Yes. And now, respect to this one again, Poisson ratio, multiply the lateral strain, multiply with axial strain, which is this one. And give the minus because that's shrinking. The same thing, this is the lateral strain, which is equal to Poisson ratio multiplied with axial strain, and with the minus. We can practice one more time. I want to save the space, so probably you can draw one more time of the cube, but let me work on my things here, utilize so right now we're working on in the z directions. In the z direction, we have loading PZ, we have a loading PZ. And now for this case, z is our axial direction, so let me label it. This is our axial direction. So in the axial direction, let me utilize this unit model again. So sigma z will be equal to E times epsilon z. So therefore, epsilon z will be equal to sigma z divided by E. This is our axial strength. So write it up here. Sigma z divided by E. And what is sigma z? Pz will induce sigma z. Right? And that calculation is simply Pz divided by A. Equal to sigma. Okay? So now for the two, again, for this one, that is the lateral strain, Poisson ratio, multiply with the axial strain, and get a minus because of shrinking. And the same thing, Poisson ratio, sigma z, minus. Are we okay? So right now, for each loading case, we have each row. And now for our situation, if for general 3D loading conditions, so that means let me use the same material model and let me define the coordinate systems x, y, z. For the general 3D loading case, that means in x, y, and z, we assume this kind of loading. For example, this is px, this is py, and this is pz. So that means in all the directions, we could have the loading like this. So Hooke's law for this condition, basically, this one can be decomposed into three loading types. Loading case in x direction plus the loading in y directions only plus loading in z direction only. So individually, this is a loading in x direction for the first row. The loading in the y direction, that is the second row. The loading in the z direction, that is the third row. And now this is a general, so that means we take the superposition principle. So for the general loading case, we simply take the summations. Summations of each loading case. So that means summation of the three things together, this will be the total strain plus the three terms together, that will be the strain for that general loading case. Are we okay? That is straightforward. And then let me write it out, the equations. For strain, again, that is due to the loading of the three conditions. And then basically here is the summation of the three terms. So this case is, let me write it out, that is sigma x E minus mu divided by E sigma y plus sigma z. And now again, for the loading in the y directions, so that is this case, sigma y will be equal to, let me take this term as the leading, for the leading positions, sigma e, and minus the remaining two terms. Let me group the two terms into this, sigma x plus sigma z. Okay, and then finally, we come up with this one, sigma z. Sigma z, and again, let me put this term at the leading positions, sigma z divided by E minus mu over E sigma x plus sigma y. So this tells us is the relation between the strain and the stress for the three-dimensional most general loading case. This question called generalized Hooke's law for 3D. You don't have to memorize this equation because whenever you want to use it, you just simply look up the textbook. in exam, I will provide this solution. I will provide this equation to you. Okay, so your learning objective is to learn, you have to comprehend what is the reasoning behind these tables. And that is more important thing than memorize the equations. Okay. In general, Hooke's law will also consider thermal deformation. So for the thermal deformation, that is just additional loading type. So usually we write it up this. The CDE, the coefficient of the thermal expansion, multiplied with temperature. Temperature is a thermal loading. Okay, and the thermal loading usually is homogeneous isotropic. So that means it's simply added up in each of the directions. That is a very straightforward additional things like this. This is called a generalized Hooke's law. And with this equation, I will keep this one here, and I can write up some examples. We can practice that equation. The first example, just to practice Poisson ratio. So if we consider a uniform rectangular bar, and the corner systems is, this is X directions, Z direction, and Y direction. And for example, this bar is under the loading 80 kilonewtons in the Z direction. And the dimension in the Z direction is 1.5 meters. And this is 50 millimeters. And this is 100 millimeters. So we have all the dimensions. We given E equal to 200 GPa, and Poisson ratio here is 0.32. We're going to calculate the deformation in X direction, deformation in Y direction, deformation in Z direction. Most of the metals, Poisson ratio is about in the range of 0.3, 0.25 to 0.35 for most of the metals, just kind of give you some ideas. So right now, let me write it up. Our model in Z direction is like this. So this is 80 kilonewtons. In Z direction. So therefore, that is very straightforward. Deformation in the Z direction basically is equal to, that is a formula we know. For example, that is deformation equal to the strength multiplied with the dimensions in the Z. So in the Z direction, that is, let me call this L equal to 1.5. Okay. And furthermore, the strain in Z basically equal to stress divided by E. Okay. And what is stress? Stress equal to P divided by A. And this is L. So basically, this is what we familiar with PL over EA. Our equation PL over EA for the axial deformation actually is coming from Hooke's law. Okay. So for this calculation, we can calculate delta Z equal to 120 millimeter. Not millimeter, 120 times 10 to the minus 6 meter. 120. Okay. And we can calculate this. Basically is the dimensions, the dimension in the y direction multiply the strength in the y direction. And let me plug in the number. Dimension in the y direction equal to 50 millimeters, so 0.05 meter times epsilon y. And this is the dimension in this is x. This is dimension in x direction. So dimension in the x direction is 100 millimeters, 0.1 meter times epsilon x. So now as long as we can calculate, we know the strength in the x and y direction, we solve this problem. And what is this? Using the Poisson ratio, we can calculate epsilon y, the magnitude of the epsilon y equal to the Poisson ratio multiplied with the axial strength. Right now, z is our axial direction, so axial strength is z. Okay, so that one is 0.32. And what is axial strength? Axial strength equal to, what is axial strength? Here we can do quick calculation. Axial strength basically is equal to the deformations divided by the length of in the z direction. So we calculate the deformation is 120 times 10 to the minus 6 meter divided by length is 1.5 meter. So this one is 80. Okay. So we plug into here. So basically this is 80 times 10 to the minus 6.
Could you include units in your calculations as well?
Good. Okay.
Track.
Yes. Okay.
What?
Strength has no unit.
Okay.
And this is a deformation has unit. This is length with a unit.
Okay.
Yeah, that's all.
How did you get the equation for epsilon y equals mu times
Yes.
epsilon z?
Yeah. So how to get this one? That is from our Poisson ratio. By definition, Poisson ratio equal to the magnitude of the lateral strength and magnitude of the axial strength. And for this case, the magnitude of the lateral strength is y or x, and this is z. Okay? So the same thing, magnitude of epsilon x, that is the lateral strength, mu times epsilon z. Okay, so the Q should have the same numbers. This is, let me use a different column. So this is 25.6 times 10 to the minus 6. And the same thing, this is 25, 10.6, 10 to the minus 6. Okay, so right now we have this. We simply plug in. So this is 0.05 meter multiplied with 25 times 10 to the minus 6. So this calculation is in y direction is 1.28 times